welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at an applications really of the Fundamental Theorem of Calculus, and we're just abbreviating that FTC. So let's do a quick review of what that says. One of them says that if capital F of x is equal to the integral from a to x of f of s ds, then the derivative of f, capital F, with respect to x equals f of x. Okay, that was the first one. And then the second one said that if f exists, capital F, oops, let's do it this way, capital F exists, then the integral from a to b of f of x dx equals the antiderivative evaluated at b minus the antiderivative evaluated at a. And what I'd like to do today is show you something that puts that adds a level of intricacy to our fundamental theorem of calculus. And what that is this: what if? So let's consider this. What if a and b are functions? So we'll make them functions of t. Are functions a of t and b of t. How does that change the fundamental theorem of calculus? Okay, so let me fix that. Well, let's see what happens. So, in other words, now, what I want to show you is this: if we take the derivative with respect to, we'll go use t here, from a to x of f of, oops, make that an s. Oh, I've got my variables all confused. Goodness gracious. Let's just use x. How about x dx, the integral from a to x of f of s ds. Well, remember what this is really just saying is that when you take the integral of f of s, you're going to get, from a to x, you get capital F of x. But then we already showed that you just take the derivative of that and you get back to f of x. Well, that's really handy. It saves us a lot of calculations, because really the derivative undoes, if you will, the integral, and so we don't even have to calculate in that situation. But watch this. Watch what happens if we're going to take the derivative with respect to x of the integral, and we'll make this, let's make it t this time. Derivative with respect to t, a of t to b of t. And then we'll do f of t, yeah, that'll work. F of s ds. Well, in this case, what we know is we know that we're going to take the derivative, but before we can do that, now we're going to create a function. So this becomes the derivative with respect to t of capital F of b of t minus capital F of a of t. It's a lot to keep track of. We're using the second statement here. The second statement of the fundamental theorem of calculus. We're just using this. But now when we take the derivative, well, the derivative of capital F is lowercase f. We already know that. So now we have f of the b of t. But remember, this is a composition of functions, and so the chain rule says we still need to take the derivative with respect to t of b of t. And when we take the derivative of capital F of a of t, we're going to get minus lowercase f a of t times the derivative with respect to t of a of t. So the fundamental theorem of calculus takes a little bit of a twist once we start adding our limits of integrations being functions now. But what happens if we turn this around? Do we get the same outcome? What if we take the integral from a of t to b of t of, now we're going to take the derivative with respect to t of f of t dt. Okay, that's probably too many parentheses, but that works. Well, now think about what happens. Now we take the derivative of capital F. So this is going to be the integral of a of t to b of t. Now the derivative of capital F, that's lowercase f of t dt. But now you can use the fundamental theorem of calculus, and it says, well, this is just capital F evaluated at b of t minus capital F evaluated at a of t. So notice that you actually get a different output when you do this. So just to show you how this works, I've kind of set up a little example here for us. We can try it. We'll take a look at an example and see how that works. So for example, what if I try this? What if I take the derivative? Let's see, I have this worked out. The derivative with respect to x. And this is a kind of a silly example, but it's just so we can see what happens. What if we take the integral from 2x to the sine of x? And let's make this t squared dt. There we go. All right, well, when we integrate t squared, we're going to get 1/3 t cubed. So let's see, we'll deal with the derivative here in a moment. So then we're going to get our 1/3 t cubed, and then we evaluate it at its upper limit, so that's 1/3 times the sine of x cubed minus, we're going to have a 1/3, and then our t cubed, the lower limit is 2x, so that's 2x cubed. And then when we take the derivative, well, we take 1/3 times 3, so that's going to be 1. Then we're going to be left with the sine of x. We reduce the 3, so it becomes a 2. And then the derivative of sine, that's cosine of x. Minus, and then we take the derivative of the 1/3 times 2x quantity cubed. Well, that's going to give me a 2x squared times the derivative of 2x. Okay, and then we can do a little bit more cleanup, but really what we want to do is see the comparison here. So now let's just change the problem around and say, well, what if we're taking the integral from 2x to sine of x of the derivative with respect to x of t squared dt. Okay, well, what happens? Well, now if I was to first take the derivative of t squared, well, this would give me the integral of 2x to sine of x. The derivative of t squared, well, that's 2t dt. But when you take the antiderivative of 2t, well, that's just going to become t squared. So now you're going to evaluate it, so you're going to have t squared at the upper integral, or the upper limit is sine of x squared minus t squared at its lower, which is 2x squared. So notice that the answers do differ slightly in the fact that here is what you would expect. Here's the obvious portion, and it matches up with these terms. But when you take the derivative outside of the integral, the chain rule causes an extra factor on each of those terms. And it's actually the second example that we're going to be using regularly as our application in differential equations. I hope that helps, and thanks for watching.